we know, there we go, that with the sail in place attached to the same cart as the blow dryer, that when I turn this on, which way will it go?
Nowhere.
Okay. Now, I remove the sail, if you will. Stay put. Which way will it go?
Left.
Nowhere.
Left. I was right. Give me
Okay.
a cookie.
Why didn't you say nowhere?
Because we have to work on
What was it pushing off of?
the air.
The air outside. When I have the sail in place, well, first of all, let's break down the action-reaction pairs. If this were not duct taped to the cart and I turned it on, it would want to blow itself off of the cart. When it's duct taped to the cart, it's wanting to push the cart that way. It's pushing against the air. But now when I put the sail in place, this board, it pushes against the board. So this part is trying to push the cart that way. The sail is capturing that force of the air, and it's pushing the cart the opposite way, equal and opposite. Okay? And again, with it on, no motion. When I first built this, I didn't have it go all the way down to this part, and some of the air escaped from underneath, and it was going that way. Because it was that air that was escaping underneath was pushing off the air here. If I could give that air that's blowing out right in here something to push against, I could still make it go. Let me show you. That thing that's pushing against has to be off of the car. You see that? You don't see that it's moving that way? Ruben, it's going that way. Okay. It's pushing off of this. I'm holding this. I'm not a little miniature person sitting on the car. So it's pushing on something off of the car. Okay? Make sense?
Yes.
All right. Moving that way. Simple machines. The purpose of a machine, any machine, no matter how complicated it is to perform a task that is too difficult, tedious, or dangerous for a human. So difficult would be, Marissa, lift 1,000 pounds and put it up on this table. 1,000-pound dumbbell and put it up on this table. Too difficult. Tedious. Matt, you're going to work on an assembly line screwing nuts onto bolts all day long. You pick up the bolt, put on the nut, pass it on. Pick up the bolt, put on the nut, pass it on. That's going to get a little old after 8 hours. So we have machines that work assembly lines, you know, robots that put together our cars for us. Dangerous. You're going to disarm a bomb or something. What if it goes off? You don't want to blow up. You use a machine. These machines take advantage of principles of physics to make the task easier. Okay? Complicated machines, no matter how complicated they are, from a car all the way up to the space shuttle, they're just simply a collection of simple machines put together. They just get more and more complicated as we add more and more simple machines to the mix. And that's what you're going to do. You're going to be building a machine, a Rube Goldberg machine, that's made up of a bunch of these simple machines. So today I want to teach you what those simple machines are, how they work, how they make our life easier. Now I notice a lot of you are being good students. You're diligently writing everything you see up there down. I want to be honest with you. If you just write the stuff that's up there down, you're probably going to not understand what I want you to understand. Okay? Some of it is going to be in yellow to stand out. Those are key terms and concepts. Those certainly you want to get down. But it's not always useful to just copy down word for word what you see up here, because a lot of times you leave out what I've explained and you fail to put it into your words. So I'm going to be blacking you out like I am right now a number of times, just so I get your attention and you can get the concept and realize it's not just about the words that are up there. Okay? Machines. Value of the machine. Man, you sure notice it when it involves doing hard, heavy work. When I worked for my brother-in-law, did concrete and cool decking, I had the label of laborer. Sounds glamorous, doesn't it? Very glamorous. The laborer is the lowest of the low in that work crew. You go out there, you're going to pour some concrete or whatever, footers for a house, and they say, here's your axe, your pickaxe, here's your shovel. I want you to dig a trench this wide and this deep all the way around, okay, this huge property. Well, 8 hours later, you've dug the trench and your back is aching and you're kicking yourself, wishing that you were a machine, because they can bring out a machine and do that job in about half an hour. So why were they having me do it?
So that America's not unemployed.
No.
Cheaper.
Cheaper. You got it. I was being paid $3.20 an hour to dig trenches like that, and I was happy to get paid it. They would have had to pay a lot more, $150 a day or something like that, to rent the machine. It was just easier and cheaper to have me do it by hand than to rent the machine, okay? And to keep America employed. Yeah. America, job one. Okay. So my point is there are tasks that are too tedious and too difficult, or simply we don't want to do, and that's why we have machines. But the thing that makes the machine able to do the task are principles of physics, like mechanical advantage. That's one of the main concepts we're going to talk about today. How a machine's able to accomplish something that otherwise would seem impossible because they use principles of physics. Mechanical advantage is one. Newton's laws that we talked about are all principles of physics that are real important to understand. Here is your first machine, and it's probably not what you expected. Let me show you here. Your first machine. Ooh. Ah. It is a board. Are you bored yet?
Yeah. Yes.
Okay. This board, you're not supposed to say yes to that one. This board is what we refer to as a plane. It's a flat, even surface. And believe it or not, it can function as a machine. I mean, just because we have a board doesn't mean we have a machine. It has to do some work. And this can function as a machine if we tilt it like this and we move something uphill or something comes downhill on it. Depending on whether we use it going uphill or downhill, it is either an incline or a decline plane. Okay? Not every ramp that goes left to right is an incline plane. If we're going down it, it's a decline plane. We've got both upstairs and downstairs around McGee, right? Well, I got news for you. You know those ones that are labeled upstairs only? They work when you go downstairs. I tried them out one day when no one was around, and they work. They do. You can go the other way, and they still work. Okay? An incline plane and a decline plane are basically the same thing. It's just a matter of which way we're going on them. Everybody got that? Okay. The word plane comes from this flat surface. An airplane used to be called aeroplane. You know, the two flat surfaces sticking out, known as wings. A plane is this thing that you use in woodworking, that you run across the wood to smooth it out. A lever takes a plane and it goes a step further. You guys think of a lever as like a teeter-totter or seesaw. So you start with this plane, and then you add some things. I'm going to get your attention here, and then I'll let you write stuff down if you need to. Again, guys, it's not a matter of just writing down word for word what's up there. I want you to get the concept. I want you to put it into your words. I take my plane, and I give it something to sit on, like this little block, this triangular block. It's like a teeter-totter now, okay, a seesaw. And then I have to lift something with it. I'm going to take some weight or something, I'm going to put it on one end, and then on the other end I'm going to apply a force. Those three things are crucial in identifying how the lever works and the type of lever it is. This particular one that I just showed here, this is referred to as a first-class lever. We'll get to each class here in a little bit. But I'm taking weight and I'm putting it on one side. That's going to be my resistance. And I'm putting the block in the middle. That's my fulcrum. And then I'm going to apply my effort here to the other side. Okay? So I have fulcrum, resistance, effort. The thing that's important to look for is what is in the middle. based on what's in the middle of my lever, I can determine the type of lever I have. And there are 3 types, okay? This is the first one. So again, if you look up here, the lever is determined by where the fulcrum, the effort, and the resistance is. Effort is the force applied to the lever, trying to get the work done. Resistance is the thing we're trying to move or lift. And the fulcrum is the point where that lever tips back and forth on. In my case, it's this little triangular block. So the standard lever that you guys are probably already familiar with, the seesaw, the teeter-totter, it's called a first-class lever. First-class lever always has the fulcrum in the center. That's the point that it's going to pivot on, okay? Resistance on one end, effort on the other. I could flip-flop this. I could put, my resistance on this side and my effort on the other side. And it would still be a first-class lever because the fulcrum is in the middle. If that's a first-class lever, then this is a second-class. Notice what's in the middle. The resistance is in the middle. Some of these levers you're going to look at and you're going to be like, that doesn't make any sense. Why would you ever want to do that? And you'd be surprised how often you use some of these. So, in my second-class lever, I move the fulcrum to one end, like I'm going to move it down to this end here, and I put my resistance in the middle, and my effort is over here. That is referred to as a second-class lever because the resistance is in the middle, effort on one end, fulcrum on the other. And I could flip-flop the fulcrum and the effort and it would still be a second-class lever. So you probably guessed what a third-class one's going to look like. Effort's going to be in the middle and the fulcrum and resistance are going to be on opposite ends. Effort in the middle and the fulcrum and resistance are on opposite ends. This is the weirdest one of all. You'll be like, why would you ever want to do that? Why would you want to have an arrangement like this where you've got a fulcrum and then you're lifting in the middle? And surprisingly, this one's very common. This one you personally use more than you probably realize. Okay, so that would be a third-class lever. I've given you a little trick here to memorize these by. If you just go by what the middle word is, or the middle thing, in this case it's effort, E is the third one, R is the second one, and F is the first one. You just remember that order. F, R, E, 1, 2, 3. F, R, E. So that way you can always come up with which kind of lever it is. First identify where the fulcrum, effort, and resistance are, and then whichever one is in the middle, if it's F, it's first, if it's R, it's second, if it's E, it's third. F, R, E. It's that simple. Now that you know these, let's see if you can identify the kind of lever you're looking at here. First, second, or third? So effort's here at the hands, the resistance is the hay bale, and the fulcrum, the pivot point, is the axle on the wheel there. Okay? It's not always a little triangle for the fulcrum. In this case, the whole thing, the whole lever, this whole lever pivots around that point. So if the resistance is in the middle, you're right. It is a second-class lever. What about this one? Third-class lever. Effort's in the middle. Now, fortunately for you, these are all labeled. That's not always going to be the case. When you make your own levers and you have them in your machine, you're going to have to look for where do we actually apply the force. And when she's doing her tennis serve, that force is applied by the muscles between her shoulder and the tennis racket. So that's going to apply that force. The resistance is the ball hitting her racket, and the fulcrum is her shoulder joint. That's where it pivots around. The lever pivots. A lot of sports skills we do are with a third class lever. The one that when you looked at it here, you thought, that doesn't make any sense. What about this? First class, just like a seesaw. We've got resistance on one side, effort, the hands on the other. The resistance is the paper we're trying to cut through. The fulcrum is the hinge on the scissors. Okay, our next machine is the wedge. Some of these descriptions, these definitions, just make it really confusing. You could write that. A wedge consists of two inclined planes placed back to back. Or you could just remember that a wedge is a piece shaped like a wedge, shaped like a triangle. Okay? It is like my incline plane, except instead of just being a flat board, it's three-dimensional, right? Three-dimensional piece. We all know that a wedge like that is going to make the job of splitting the log easier. The question is why? You might say because it's sharp and it's pointy. Yeah, but why do sharp, pointy things go into wood easier than things that are blunt? That's the physics principle we're going to look at here in a little bit. A screw. Now, who would think that a screw, like you would use to fasten wood together, would actually be a machine? Well, it very much functions like a machine when you are putting it into the wood. But there are occasions where we take a screw, and we have a giant version of one, and we use it just like that as a machine. That definition gets kind of confusing too. It says an inclined plane wrapped around a tapered cylinder.
You have to say taper. Like, what does that mean?
Well, that's what I'm going to explain. Okay, so here's the cylinder. This rod right here is the cylinder, right? When I say tapered cylinder, that means it comes to a point. Like when you take a stick and you sharpen it to a point. That would be a tapered cylinder. So that is the basis for a screw. Then around the screw we have those threads, they call them. Okay? The threads, if you start and you walk, if you were a little tiny critter, you could walk along those threads. They would spiral around the cylinder all the way around till you wound up on the opposite end. Okay? They're like a little miniature spiral ramp. Okay, you guys know what spiral staircases look like. Well, here's a spiral ramp. In New York, they have a museum called the Guggenheim. And it's a round building, and you walk in and you walk up a ramp. And you continue up that ramp all the way around. It travels like a spiral throughout the building, all the way up. And so you never have to step up steps. You're always just walking up this ramp. When you reach the top, you just turn around and go all the way back down. It's great because you don't get lost. So that tapered cylinder goes right in the middle, and that's how a screw is made. Okay? So you got to always have a pointy end on a screw. A lot of people confuse screws with bolts. Bolts don't have pointy ends. Screws do. Okay? And so you get that point stuck in the wood, and then as you turn it, those threads cut and bite and pull the screw into the wood. It's very ingenious. So that's all that's trying to describe. If you know what a screw looks like, and that the threads, if you follow them, they take you to the opposite end, you don't need to write down that description. What I did want to show you here, though, is how a screw can, by itself, function like a machine. The one you see on the left there, and also an illustration of it here on the bottom, that is known as an Archimedes screw. You remember Archimedes?
Yeah.
Which guy is he up here? Zach?
He's the clay guy.
He's this guy, way over here. That's Archimedes, the clay guy, yeah. He's the one that we didn't have a photograph of or even an illustration. We have a sculpture of him. Okay? He's the one that ran down the street naked screaming, "Eureka, Eureka, I found it." He's the one that established Archimedes' principle that's important in a lot of things, from airplanes flying to boats floating. He created the death ray and all sorts of other things used in warfare. But this is an ingenious design. This screw isn't used to hold things together. It's used as a pump. Head up, Matt. You stick one end of this down in the water, and then as it cranks, as it turns, the threads cut in and they get a bite of the water, a gulp of water. And as they continue to spin, they raise that water level up to the next level of threads, and so on and so on. So it brings that bit of water to the top, and then it just falls off into this container. It's a very clever design. You just have this single moving part, the screw, and then this little trough that it sits in. They still use these today for irrigation. It's a very simple design for a pump. Other pumps that we use, you know, like in your cooler or so forth, they have a lot more than one moving part. So that's the cool thing about these, is they're very reliable. Wheel and axle is a simple machine. It says a wheel and axle consists of two circular or cylindrical objects that are attached together and rotate around a common axis. Okay, I'm already confused. You probably are too. Believe me, I tried to write that as clearly and as accurately as I could, and it just sounds really confusing. That's why you need me to talk about it. That's why I don't just give you a handout of those, because it won't help you by itself. Which of these two things is the axle? The big or the little?
Little.
The little is the axle, okay? And what that was describing is two cylindrical or circular objects. Circular object, the wheel. Cylindrical object, the axle. Connected together, and they share a common, now here's the big phrase, axis of rotation. Here's what it means, okay? When I spin this wheel, it spins around a point right here. That's what we call the axis of rotation. When I spin the axis, it spins around a point that's right here, which happens to be the same as this point. So they share that point. When I spin this pair, they share a common axis, a common point of rotation. Sometimes you spin the axle and the wheel goes with it. They're connected together. Sometimes you spin the wheel and the axle stays put. But they all share a common point of rotation. That's what they have in common. Yes? Yes. The middle of the spin, of whatever spins, yes.
So the axis what?
Axis of rotation. Believe it or not, this is a wheel and axle. This would be the wheel, and this would be the axle. Two cylindrical or round cylinders, okay, that share a common point of rotation. So as I rotate, I spin the screwdriver, the center of that shaft there is the point of rotation. As I turn the handle, the center of the shaft is the center point that it rotates around. So they share that point. This works, a screwdriver works like a wheel and axle does. Now we're going to talk about how it gives you a mechanical advantage in a little bit, but what I wanted you to get right now is just what's what. By the way, a lot of people confuse tire with wheel. Tire is the rubber thing that goes around the outside. This is the wheel. What they call is the rim. The rim is the thing that the wheel actually rests in, right in there, that groove. Okay? The axle's the smaller thing that goes in the middle. Sometimes we have power, like in our car, is attached to the axle and the wheel turns. Sometimes the power is given to the wheel, like in the screwdriver, and the axle turns. Just depends on what we're trying to accomplish. The pulley. It says a pulley consists of a wheel and axle with a grooved rim around which a rope, string, or cable is strung. In some cases, the pulley moves with the effort. In others, it is fixed. So we start with the same kind of arrangement, a wheel and an axle, but instead of having a tire around it, we have this little groove. And we take a string, a rope, a cable, and we put it over that thing, and as we pull that cable, this spins. Sometimes it moves with the thing we're trying to lift. Sometimes it stays put and it just spins in place. That's the difference between a fixed pulley and a movable pulley. You can see here on this one, here's the weight, we pull on this cable and the pulley stays put. On this one, when we pull on the cable, the pulley moves with the weight. That's a movable pulley. So a quick little illustration of each and you should be good. Next machine, a gear. We start again with just a basic wheel and axle, but we cut little teeth, little notches into that wheel. And a gear is really only useful if we have at least two of them together, like you see here, like you see behind me. You turn one gear one way, and the other gear connected to it goes the opposite direction. So gears always do one of two things, or sometimes they do both. They can change the direction of the motion. I turn the big gear clockwise and the little gear goes counterclockwise. It changes the direction. The second thing gears can do, what we take advantage of when we use them on our bike or in our car, is they can change the speed of the movement. So maybe you're pedaling way too fast and you don't need to pedal that fast. You can change the gear on your bike so you pedal slower. If you look at this one as an example here, you'll see that as I turn the little gear one full turn, did the big gear go one full turn? No, went a little more than half. We'll look at that again. The little gear goes one full turn, and the big gear goes a little more than half. So these two gears that are connected together, because one is big and one is small, are going to move at different speeds. That way, if I am moving really, really fast on one gear and I want the other one to go slow, I can do that. I can accomplish that. So I don't have to pedal super fast, or vice versa. I can change the speed that I'm going to get out of my machine. Alright, now we're going to go back, we're going to look at each machine and we're going to talk about how it gives you an advantage. And before you write all this stuff down, let's just talk about the basic concept here. Machines are supposed to do work. And believe it or not, there is a formula for work. The formula for work is force times distance. Force times distance. In some cases, we apply a lot of force and we do it over a short distance. In other cases, we might apply a little bit of force and do it over a long distance. If it comes out to the same number, we've done the same work. Let me give you a little puzzle here to solve. See if you can solve this before we get into the rest of that. I have a 1,000-pound barbell on the ground there, Matt. My challenge for you is to come up with a way of getting that 1,000-pound barbell up here on this table. How would you do it? I don't know is not an answer. Give me a guess. What are we talking about here? Okay, use a lever is a good idea. What if I said you can't use any machines? Anyone in here able to get that 1,000-pound barbell up here on the table?
No.
You all give up, huh? Zach?
Work as a team.
There you go. Any individual in here that could accomplish that? I know I could. And I don't even need another machine. I can do it all by myself. You give up? This is too hard of a riddle for you guys, huh? Huh?
It's 1,000
1,000 pounds.
pounds. Unless you're me.
You guys know what a barbell looks like? Ah! You get the star. Good job, Bethany. So, she said, take it apart. If you've ever looked at a barbell, you know that you've got this pole, the bar, and you've got plates that go on the end, and then you put a collar over that to keep the plates from falling off, so when they lift it up, it doesn't fall off, right? Well, there's two ways of getting that 1,000-pound barbell up here on the table. Method number one, you pick it up in one fell swoop, you clang it down on the table, right? You did the job, you did the work. Method number two, take the collars off, pick those up, put them up here. Take one 25-pound plate off, put it up here. Take another one, put it up here. Take another one, put it up here. Until you get all of them up there and the bar. In both cases, you accomplished the same thing. You got the weight up here on the table. You raised it up however high this table is. In the first example, you applied a tremendous force, and you did it over a short distance. Boom, boom, I'm done. In the second example, what Bethany came up with is you applied a much smaller force. You only had to lift 25 pounds at a time, right? But you did it over a long distance. You had to grab a little bit, go back. Grab a little bit, go back. You had to make all those trips. Do you see that? In both cases, you did the same work. Back to this. Let's see if you can understand. Forget about this right now. Work equals force times distance. Okay? In the first example, you applied a tremendous amount of force. And you did it in a very short distance. Okay? So let's just say 1,000 newtons of force over 1 meter. In the second example, you only applied 1 newton of force. But you did it over 1,000 meters. Because you had to keep going back and forth, right? 1,000 times 1 equals? 1 times 1,000 equals? 1,000. Do you see how we did the same work? That's how these machines work for us. That's how they cheat. That's how they make the job easier. Is they take the force required and they spread it over a longer distance. That's it. When you hear the word mechanical advantage, think about what you have to put in compared to what you get out. Okay? If I have to put, let's say this is 1 kilogram weight. I have to apply a kilogram's worth of force to lift this. I don't have any advantage. Okay? There's no mechanical advantage. What I put in is what I get out. Okay? If, however, this weighs 1 kilogram and I only have to apply half a kilogram to lift it, I have an advantage. I put in less force than I got out. Okay? The way we accomplish that is we have to do it over a longer distance. So when you look at machines that make it so that you can lift something far heavier than you normally could, how they give you an advantage, they make it easier. This is how they do it. You have to apply the force over a longer distance. You're not getting something for nothing. This formula for mechanical advantage, output force divided by input force, it doesn't take into consideration distance. Okay? Yes, it does give you an advantage, but you had to do the work over a longer distance, probably for a longer time. Remember how I talked about how my dad would beat me in arm wrestling? He'd have his fist here close to himself, and mine would be all stretched out. I'd be out like this. He would always win because he had a mechanical advantage. He had leverage. He was closer to himself, and that gave him a mechanical advantage. I had a mechanical disadvantage. I was never going to win. Now let me show you how we actually calculate these things. Let's use an example here. Let's take the the incline plane as an example. Several ways you could get that box into the back of the truck. Method number one is sitting here on the ground. Go over, pick it up, put it in the back of the truck. Method number two, put it on a dolly like this, a hand truck, roll it up a 3-meter ramp. Method number three, put it on a hand truck, roll it up a 6-meter ramp. Which one's going to be the easiest? Which one? The 6-meter ramp is going to be the easiest. Which one requires you to move it the longest distance? The 6-meter ramp. Which one did the most work? They're equal. Who said that? I heard someone say that. You didn't say that. It's one of the girls back there. They're equal. Yes. Look at it this way, guys. 3 times 2 is?
6.
2 times 3 is? 6. Okay? That's all I'm doing is I'm changing. I'm either going to put a little bit of force over long distance or a lot of force over short distance. Lifting that box straight from the ground into the back of the truck, boom, it's done over a very short distance, required the most force. Rolling it up a ramp is certainly going to be easier, but now I got to move it a longer distance, 3 meters. And this is why moving trucks have the nice long ramp. Okay, because if it had a short ramp, you'd get your washer and dryer halfway up there and then it would start rolling back on you. Because you'd need more force. The longer the ramp is, the less force you need. Okay? Why don't we make the ramp super, super long?
So you have less work.
Well, yeah, there's a point where we're going to have to go so long that it's just a waste of energy. We don't need to make it that easy. You can roll most stuff up this 6-meter ramp. That's actually quite long ramp. Very long ramp. But this particular ramp, because it's twice as long as that one, and they're both lifting the box to the same height, this has twice the mechanical advantage. Okay? It's going to require half the force. What you put in compared to what you get out, twice as much as this. This requires twice as much force. And that makes sense. I mean, you're pushing a refrigerator up this, you're going to have to push a lot harder to get it up this ramp than you will this one. Even though it reaches the same point, this seems a lot steeper. Do you see that? That's how that works. How many think they understand how to get this mechanical advantage? Good. The same thing is true for a lever. We look at where the fulcrum is compared to the effort to determine our mechanical advantage. So here you can see the fulcrum is very close to the effort. Here it's very far away. Which one's going to be harder? Harder for you to push down on. The bottom one. This is going to be a lot harder for you to get going than this one. Let me show here with this example if you can see around the computer here. So I'm going to take my fulcrum and I'm going to put it right smack dab in the middle. Just like you would on a teeter-totter. Now if this were a teeter-totter, a seesaw, you would have, one kid on this side, the other kid on this side. If they're the same weight, it should be nice and balanced, right? Because that thing is right in the middle. However, if you take that thing, and some seesaws you can kind of move a little bit to compensate for that. If you take that thing and you push it farther away from, let's say you're the one over here applying the effort. You push it a little further away. Now, do I need this whole 1 kilogram weight on this end to make that go up? Is that required? Do I need this entire amount? No. I can lift that quite easily with a lot less, Bethany, with a lot less force. Just using my pinky, and it's very easy to lift. Okay? But there is a trade-off. Yes, it takes less force now than it did before. I don't need the whole 1 kilogram weight. But what do I have to do? What's the trade-off here? Excellent, Matt. You have to go a longer distance. Look at how far I have to move this end to raise that to level. Okay, I had to go like that far to raise that up to level. Now, if I put this closer to me, I don't have a mechanical advantage, I have a mechanical disadvantage. Will 1 kilogram lift that now? Not even close. It just sits there. Okay? In order to lift it now, I have to apply a lot more force than 1 kilogram. The upside is, notice how far I had to move to lift that to level? I only had to move a short distance now. Do you see that? The farther that fulcrum is from the effort, the greater the distance you must travel, but the less force it takes. The closer it is, the more force required, but the less distance you have to move. Archimedes, I believe, is the one that said, give me a lever long enough and I can lift the world. it is true, it's good physics that we could lift incredibly heavy objects by ourselves with a long enough, strong enough lever and fulcrum. You could lift a car by yourself with a long enough lever. You'd have to have that fulcrum be way far away from you, very close to the car, okay? And you'd probably be about this tall. That lever would be like 25 feet over your head and be a very long lever. So you have to climb up on a ladder and then grab a hold of it, and you could lift that car, but you'd have to pull it a long, long way, and that car would barely be off the ground. Do you see what I'm saying? So you could accomplish some incredible things with a lever, but it'd have to be very long and very strong. That's all this is saying. It's talking about how the lever works and gives you a mechanical advantage. And this is showing you the same thing. Again, you see there's a trade-off. We had to go a long distance, but it only required a small force to move it. Here, on the other end, we go a small distance, but it's able to lift a large force. That's the trade-off. Because it's all about work, and work is force times distance. How much force do we have to apply over what kind of distance? Same exact principle now works for a wedge. It's just like a ramp. You know, this ramp is longer than this one, if you will, and this wedge will drive into the wood much easier. It requires less force to drive that into the wood, because the wood has to travel around the outside of a very skinny wedge. This one could theoretically split the wood faster, sooner, but it would require a lot more force to get this to go into the wood. Just like it requires a lot more force to push things up a short ramp than a long ramp. So that's the trade-off again. Yeah, this is going to be the tool you want to use, the narrow, skinny one, but that's the trade-off. Less force, more distance. Before you couldn't physically do it. You weren't strong enough. Now you can do it, but you're going to have to do it over a longer distance. All right, here's one of the more confusing ones. I'll see if I can simplify this for you. This is how a wheel and axle works and gives you a mechanical advantage. All right, so I mentioned that a screwdriver is an example of a wheel and axle. So if I could have somebody come up here, I will demonstrate. Zach? You have to stay off camera so I don't have your likeness on here, but I can have you hold this. All right, what I'd like you to do is just hold that with your hands as tight as you can, and don't let that spin, okay? As tight as you can. Got it?
Got it.
Okay. Doesn't take any effort at all for me to spin that, right? Let's look at this. If you trace the path that axle spins, it travels a very short distance. It travels a little teeny tiny circle. Trace the path that the wheel takes, and it travels a much bigger distance. Do you see that? So here, I'm having to turn this, move this wheel a large distance, and it only goes a short distance there. But the advantage is I need very little force here, and I get a lot of force there. Same thing works for a screwdriver. Hold the end of that. Okay, don't let it spin. And with almost no force whatsoever, I can spin that very easily. Because the handle is always bigger. The wheel part's bigger than the axle. This has to go a large distance, but I need very little force. This goes a short distance, but I get a lot of force out. If he tries to hold it even with the wrench, like this, hold it on like that. Again, still, I can twist that quite easily, okay, even with the wrench. But if he takes the wrench and he holds it like this, guys, okay, go ahead. Now I try to do it. There ain't no way I'm going to win that one, okay? Thank you, Zach. You can have the seat. So you see the handle? Look at how far that handle must travel to do one full circle. Look at the size of that circle, much bigger, as opposed to the size of this handle circle. You see that? So it's all about input and output force. Let's look at this again. In this case, on the screwdriver, the input force, that's you using the machine, goes to the wheel part. You have to move it a large distance. Bigger the handle, the greater the distance. But you get a lot of force here. that force only goes a short distance, which is why when you're screwing in screws, you have to do this all day long, it seems like. Because you have to go a long distance here to get a little distance there. Sometimes, believe it or not, we work it just the opposite. We're applying our force to the axle, and we're going to get the output force at the wheel. And in this case, this is actually a mechanical disadvantage here. That would be what you see in the case of a car. So you spin the axle to get the wheel to go around. You might say, well, why would you do that? Why don't you just turn the wheel? Well, the advantage is I only have to turn this axle a little bit, just a little bit, and I get a lot of motion here. A little motion gives me a lot of motion here. The downside is I need a lot of torque, a lot of force here. To make this big wheel, like the paddle wheel, to make it go around, I'm going to need a powerful engine here. Fortunately, I got a steam engine that can do the job. But again, the upside is this moves a long distance and moves a lot of water, and that's the goal. Move a lot of water, move the rubber on the tire a long way so we travel far. That's the whole idea. Okay? That's all I'm explaining here. It's just how we have that trade-off of distance versus force. A pulley, the way a pulley works, to understand how it works, first you got to count the number of rope segments, not counting the last one. Let me explain. In this pulley system, this part here, this piece of rope, if you will, of line, is the one that has our effort applied to it. It's like this one here, has our effort applied to it. To figure out what the mechanical advantage is of a pulley system, you simply count the number of rope sections, not including that one that you attach your effort to. So the mechanical advantage of this one would be 2. That means, remember, mechanical advantage is output force divided by input force. So mechanical advantage of 2 means I can lift, I get twice as much out than what I put in. Like 2 divided by 1 would equal 2. That means I get twice as much out of this than what I put in. If I could normally only lift 500 pounds, with this pulley system I could lift 1,000. That's what this is saying. And I can prove it to you, although you guys can't all read the numbers off of this. I can prove it to you right here with this setup. I have 2 different pulleys. The ones on the top would be referred to as what kind of pulley? Fixed, because they don't move. As I pull on the weight here, that pulley squeaks, but it doesn't move. On this one, I have a fixed and a movable pulley. One stays put, and the other one moves. And they have a very similar setup, but what you might notice right off the bat is that when I lift this one, I have to put in more force. The mechanical advantage of this is, don't count this, so what is the mechanical advantage? 1. I have 1 rope segment. So the mechanical advantage is 1. What's the mechanical advantage, or was, on this one? 2. So you can see that there are 2 rope segments, 1, 2, not counting the one that goes down. So this has a mechanical advantage of 2. And if I pull both of these down, if you could read off the scales, and you can see it on the computer, but you guys can't. This one is reading 8. This one, with 2 pulleys, is reading 4. It requires 4 newtons to lift this. This requires 8. Okay, but notice how this one's higher too. Do you see that? In order for me to lift this one as high as that one, I'm going to have to pull it twice as far. In order to lift this one over here as high as that one, I have to pull it twice as far. Every time you add another pulley like that, you increase the amount of rope that you're going to have to pull to get the job done. So there is a trade-off. It's not like you're getting something for nothing. You have to apply the force over a longer distance. All right, almost done. So that's the pulleys. Last ones here are the gears. I have 4 different kinds of gears shown here. This is a worm gear. I have a crown gear down here, a bevel gear there. Every time you have 2 gears, there's one gear that you apply a force to, the one that you're cranking, and the one that goes along for the ride. We have, I hope you don't have gum again, that would really be in my face. We have a driving gear and a driven gear. The one that has the force applied to it is the driving gear. The one that is pushed by that is the driven gear. And remember, like I showed you before, the size of the gear will determine the speed. You have different gears you shift on your bike, depending on what speed you want to be traveling at. If you're going uphill, you want to be in a different gear. And obviously, as I turn these gears, you turn one way, the other one goes the opposite direction. I do want you to know the difference between a driving gear and a driven gear, as well as the 2 things that gears can do for you. But by changing the size between an input gear and an output gear, you can give yourself more mechanical. You can